All right, so good morning, y'all. Morning, morning. So here's our plan. Next week, we're gonna have our next test. All right. Yeah. Should be straightforward, just a whole test on probability. All right. So you're gonna have that table, right? Or we did that, the and and the or. We're gonna have our binomial distribution, and today we're gonna finish up normal distribution, and that's gonna be on the test. And you guys are good to go. Now it'll be test two. I'm sorry. So remember we had that table where we had to find like the probability of let's say I don't know, blue or something. I'm just making it up, right? And we use a table and we put the total over the total of everything. That table, right? Contingency table is what it's officially called, right? So we have that. We have the and the or situation, right? And remember when you do the or, you're adding the two situations and subtracting out the intersection, right? And then we have the binomial distribution, right? That's with the NPR thing. We're actually going to go over a little bit of that today as well, right? And then you have the normal distribution, right? The straight calculator. Yeah, I'll be good. Mhm. Yeah. Yeah. I'm gonna make that up. What you call it after class, and I'm gonna post it in the announcement. Yeah. It might not be like right after class. I gotta go in there, but y'all gonna get it this weekend. You know? Yeah. Yeah, but before I even jump into today, does anybody have any questions? Anything I want to go over last week? Last week we did normal distribution. Well, actually, no, I'm lying. We did X distribution, X bar. All right. So long story short, it's the same process, but the formula is a little different. So the standard deviation now, right? Instead of it just being like this was our old, hold on, let me just get rid of that. This is our old Z formula. It was Z is equal to X minus mu over sigma. So last week we had Z is equal to X bar minus mu, but the standard deviation changed. Now it's sigma over the square root of n. Right? Yeah. Yeah. So long story short is a new story, and in the story, you're gonna have a sample size. You just plug it in, right? You're gonna get an answer for Z, and you look it up the same way. Nothing changes.
The X bar standard deviation,
X bar is sample mean. Yeah,
the one below it, standard.
right. Right. The sigma. Yeah. So what's happening in this one? Like in this formula, I know what the actual population mean, the actual population standard deviation is. So that's why I'm good to go with that. But in this formula, right, I have a bunch of sample means, right? And I can't definitively say that the standard deviation is being captured in each sample. So I can't put the population standard deviation. I got to divide it by how many numbers there are, or the square root of how many numbers there are, to like kind of make it more approximate. You know? Right. The sample size. Yeah. So like it's yeah. It's actually in your formula sheet. You guys look at chapter 7 on your formula sheet, it's right there. Yeah. So you guys have everything. I'm gonna get you that practice or prep for our test, and then we'll be good to go. All right, so what we about to go over here, this will be on your test next week, all right? Well, the first half of class, the second half of class is just I don't want to waste the day, so I'm gonna teach a new topic that won't be on the test, all right? But this, what I'm about to show you right now, will be on the test. Mhm. So what we're doing today, we're kind of merging, right? Our binomial distribution with our normal distribution, right? So it's gonna be really fire. Let me show you. All right. So we're going to do a normal approximation to the binomial distribution and to the p hat distribution. All right. This is going to be really, really cool. All right, let's get it. So the probability that a new vaccine will protect adults from cholera is known to be 0.85. The vaccine is administered to 300 adults who must enter an area where the disease is prevalent. What is the probability that more than 280 of these adults will be protected from cholera by the vaccine? This question falls into the category of a binomial experiment, right? Because you're either going to get protected from the vaccine or you're not, right? With the number of trials, n, right, equal to 300, the probability of success, p, is going to be equal to 0.85, and the number of successes, r, is greater than 280, right? It is possible to use the formula, hey, morning. It is possible to use the formula for the binomial distribution to compute the probability of r, which is greater than 280. However, this approach would involve a number of tedious and long calculations, right? Because remember how when we were doing the binomial distribution, we want to do it for one or for two, it was mad work just to do for one, you know? And then this, basically what we're saying is that there's so much that we got to do here that we want to find a way to approximate the answer a little bit, you know? That's the lesson here. All right. However, this approach would involve a number of tedious and long calculations. There is an easier way to do this problem, right? Under the conditions stated below, the normal distribution can be used to approximate the binomial distribution, right? So that's our game for today. Let me give y'all toolbox that we're gonna be using for today. This is gonna be fire. This is all on your formula sheet, by the way. You know, so you don't gotta memorize everything. So look, no more approximation to the binomial distribution. So consider a binomial distribution where you have n is your number of trials, r is your number of successes, p is your probability of success on a single trial, and q, right, is your probability of failure on a single trial. Remember, q is always 1 minus p, right? That hasn't changed. Oh, this is something new right here, right? We want to have to remember this one right here. If n times p, right, is greater than 5, and, right? Remember when we use that word and, that means both, right? And n times q, which is our probability of failure, is greater than 5, then r has a binomial distribution that is approximated by a normal distribution with mu is equal to n times p, and sigma is equal to the square root of n times p times q. All right? You know what? Let's rewrite this formula a little bit. I'm gonna edit that up a little bit. Huh? Yeah. I'm getting to that. I got you. We gonna get there. I'm just laying the groundwork real quick first. Let's rewrite that formula to say it like this, right? N times P times 1 minus P, right? That makes it a little bit nicer, right? So note, as N is increasing, the approximation becomes better, right? So we remember from our I don't want to say law of large numbers, central limit theorem, right? As our n gets larger, our distributions approximate themselves to a normal distribution. That's where that's coming from. Mhm. So give y'all a minute, and then we'll jump into an example. Good. All right, let's jump into an example real quick. So we're going to look at the binomial distribution for graphs, right? So here, what do we want to do? We want to graph the binomial distributions for which P, our probability of success, is 0.25, and Q, our probability of failure, is 0.75. And the number of trials is first n is equal to 3, then n is equal to 10, then n is equal to 25, and finally n is equal to 50. All right? So the purpose of this is to show you, right, that as our n is increasing, the distribution is becoming more normal. All right. So let me show you guys real quick. We're going to start off small, right? I'm going to start off with the n equals 3, n equals 10. Take a look at that real quick. All right. So they're saying that the authors used a computer to get these. So obviously, so let's look at this figure, right? 731, right? The probability of R, remember, is going to be my y-axis. My x-axis is going to be R, my number of successes. This is a binomial distribution, right? So we know that all of our R's are in the middle of each bar, right? Remember that? Anyway, in this first graph that we have right here, right? This is for n is equal to 3, right? So we have 3 is our sample size, right? So we can have at most 3 successes here, right? And this doesn't really look like a bell-shaped curve, right? It doesn't look normal, right? But what happens when we up it a little bit, right? So let's look at the next one. The next one over here, our n is 10, right? So now it's looking a little bit more normal, right? It's not perfect, but it's looking a little bit more normal, right? So that's what happens as we increase n. Let's look at 2 more examples real quick. 2 more examples. This is going to be real good. This is going to be real good. So you see these right here now? This is for N25 and then N50. Technically speaking, right? Going back up here for a second. No, the one at the bottom. Yeah. Technically speaking, right? By our definition, our sample sizes aren't large enough to be approximated to normal, right? Because we have to have a sample size of 30 or bigger for it to be normal. So technically, 1, 2, and this one right here is not normal. But look at how close to normal it looks, right? It's coming clearer. It's getting a little bit clearer. But now look, let's look at what happens when we jump over 30. Right, when we jump over 30, this is n equals 50 right here. Oh, that's beautiful right there. Normal distribution, right? So now we could use that information to approximate what the area under the curve might be or what the probability might be, right? And that's really what we're getting into today, right? So this would be a good approximation for for the normal distribution to approximate the binomial distribution. And in this scenario right here, with n being 50 and our probability of success being 0.25 and our probability of failure being 0.75, right? We know that our n times p is greater than 5 and our n times q is greater than 5, right? That's the condition that has to be met for us to use this scenario. Okay. Let's elaborate on this a little bit more. All right, so when n is equal to 3, the outline of the histogram does not even begin to take the shape of a normal curve. But when n is equal to 10, 25, 50, it does begin to take a normal shape indicated by the red curve, right? Excuse me. From a theoretical point of view, the histograms in figure in the first 3, as I was saying, right, would have bars for all values of R from R equals 0 to R equals n. However, in the construction of these histograms, the bars of heights less than 0.01 units have been omitted. That is, in this example, probabilities less than 0.01 have been rounded to 0, right? So basically, I can show you with this graph, right? You know that technically, right, these are our successes, right? And remember, in the binomial distribution, we're going from 0 to n, right? So we're going from 0 to 50, right? So what they're saying is, you notice how this thing just starts at a little bit before 4 and it's ending at 22, but we actually are going all the way to 50, all the way out here, right? So those probabilities are so small, we just call it a 0, right? So you're gonna notice when you do it in your calculator, you might get an answer that says blah 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 e to whatever power, right? That's a very, very small number, right? It's so small that you could just literally call it 0 and call it a day. Right? That's what that's saying. Right there. All right. If it's okay, I want to jump into another example. All right. This one we're gonna have more of a story though. So this is a normal approximation. All right. Let's check this out. The owner of a new apartment building must install 25 water heaters. Damn, no hot water. From past experience in other apartment buildings, she knows that Quick Hot is a good brand. A Quick Hot heater is guaranteed for 5 years only. But from the owner's past experience, she knows that the probability will last 10 years is 0.25. So here's our question right here, right? What is the probability that 8 or more of the 25 water heaters will last at least 10 years, right? And then we're going to define success to mean that the water heater will last at least 10 years, right? Good stuff, good stuff, good stuff. So if the probability that it will last at least 10 years, right, is success, right, then we know that this value here, that's my what? In terms of NPR, what is 0.25 going to be? 25%, right? So that's my P, right? This will be my P value. What is, let's pick out another one. What's 25 up here? What's that? Sample size, right? Number, right? Both correct. So that's going to be your N right there, right? And then that being said, what's my X? Not 10 years. Mm-hmm. 8, right? So what is the probability that, oh shoot, wrong thing. Sorry about that. Sorry about that. Let me try it again. What is the probability that it will be 8 or more, right? So 8 or more will be your probability. Right?
So you were at MP is greater than 8.
N times P is greater than 8? No. I want to do the probability that X or whatever will be 8 greater than or equal to 8. Yeah, that's what this is doing. As long as you can identify the pieces of your question, Gucci. Gucci. All right, so let's take a look at it real quick. My handwriting not so pretty. All right. So in this example, n is equal to 25, p is equal to 0.25. So the figure, right, represents the probability distribution we will use, right? Let R be the binomial random variable corresponding to the number of successes out of n is equal to 25 trials. So we want to find, right here what we said, what's the probability of R greater than or equal to 8 by using the normal approximation, because we don't want to do all that work, you know? This probability is represented graphically, right, by the area of the bars over the 8 plus the area of all the bars to the right over to the right of the bars over 8. Let me show you what that's looking like. Excuse me. Actually, we didn't even, I don't think I got that. Just bear with me 1 second. Cool. Bear with me 1 second, real quick. I just want to bring that picture back. So this is what we're talking about right here. All right. So what I'm saying is, right, I want the area from 8 going this way. All right. Just graphically speaking, what we're trying to do. But we don't want to actually calculate that because that's a lot of work. 8, 9, 10, all the way to 25, right? So we're going to use the normal distribution to approximate what that answer could be. All right. So let's take a look at how to do that real quick. This is mad dope. So let X be a normal random variable corresponding to a normal distribution with mu is equal to n times p, right? And then remember, this is our n, this is our p. We'll just multiply them together. We get 6.25. And sigma is equal to the square root of n times p times q, which is the square root of 25 times 0.25 times 0.75, which is similar to 2.17, right? This normal curve is represented by the red line in the figure. The area under the normal curve is x is equal to 7.5, right? To the right is approximately the same as the areas of the bars of the bars from the bar over r equals 8, right? So to the right, let's notice something, right? I'm interested in the area from 8 to the n, right? But notice that this is a bar, right? The 8 is this bar right here, right? But it's not, it's like 8 is in the middle. There's still some area over here that I'm kind of like skipping over, right? That's why we approximate it to 0.5, right? Because you want to cover all of the area and push it all the way out for the bar, right? So it's important to notice that we start with x is equal to 7.5 because the bar over r equals 8 really starts at x equals 7.5. The areas of the bars and the areas under the corresponding red normal curve are approximately equal. So we conclude that the probability of r greater than or equal to 8 is approximately equal to the probability of x greater than or equal to 7.5, right? And now, once we have this, we're right back to what we were doing last week. Light work, all right? So let's just run through this real quick. Boom, boom. All right, so when we convert the x equals 7.5 to the standard units, right? Remember this formula, x is equal to, z is equal to x minus mu over sigma, right? We just plug in what we have, 7.5. We calculated our mean, which was n times p earlier, right? We calculate our standard deviation, which is the square root of n times p times q. Plug it in, boom, boom, boom. Calculator is going to give us 0.58, right? And then after that, you already know what to do, right? We took the probability of X greater than or equal to 7.5, converted it into Z, which became the probability of Z greater than or equal to 0.58. Remember, I can't look up in the chart, I can't look up probabilities that are greater. So I have to do the complement, right? One minus the probability of Z less than or equal to 0.8, and then boom, boom, right? We didn't do that though, right? Remember when we did it, we drew our distributions, right? So let's try that out real quick, right? Sorry, let me get my pen. Hey, good morning. So remember, this is how we did it, right? So we got 0.58. We know that 0.58 is somewhere like right here, right? Right? And then I want the area that's to the right of that, right? Let's take a look. Right? I want the area to the right of that, right? So then now, calculator, right? Remember that this is going out to what? Infinity over here. And we remember an infinity, right? And our calculator is 1E 99, right? So what's my lower bound going to be here? Remember when we go into the calculator, right? Go second distribution, right? Go across the distribution, and we go down to normal CDF. That's what we're doing here, right? Y'all can try it in the calculator right now if y'all want, right? So remember, you press let me get the calculator real quick. Hold on. Just bear with me 1 second. Just gotta find the picture. I got the picture somewhere. It's not it. Now just bear with me 1 second real quick. I'm just getting the calculator real quick. Just a quick recap. All right, bringing it back. Right here. We good, right? Looks a little bit clearer than what it used to be, right? So we gonna hit my red pen for this, right? Second, now we're gonna hit the data button, right? That's where it says stack regression slash distribution. All right, so second, and we're gonna hit the data, right? And then right after that, we want to go across, right? That's the next thing we're gonna do. We want to go across, just like right here. We want to go across to where it says distribution, DISTR, right? So let me just write that real quick. That's going to be DISTR, right? And then after that, we want to go down, right? This will be the down button right here. And then I want to go down to where it says normal CDF, right? That's what I'm looking for. I'm looking for normal CDF. That's what I'm looking for, right? And then when you hit that, believe, correct me if I'm wrong, the first thing that comes up is they're going to ask you about the lower bound and the upper bound. Or they ask you for the mean and standard deviation. I'm forgetting right now. Which one is it? Got you. So our mean right here, right? This is a normal distribution, right? So whenever we have our Z, which in this case we do, right? Our mean is what? What number is the mean when we have our Z? Something real simple. 0, right? So our mean is 0. And what's our standard deviation? Oops. Should have been standard deviation is equal to 1. Perfect. Right? Mm-hmm. So let me get to that. All right. So then they're gonna ask me for lower bound, right? And upper bound. In this question right here, right? Let's imagine everybody that we're just standing like right here, like this us. Right? We in between the whole distribution, right? Lower bound is to our left, upper bound is to our right. Right? So what's the lower bound here in this picture? It's positive. What's the number? 0.58, right? So that's gonna be my lower bound. And what's my upper bound gonna be then? Right? It's gonna be my infinity. Right? And remember that should already be there, right? But if it's not, remember it's 1E 99. Then you just hit enter, right? And when you hit enter, you're gonna get an answer, right? Verify. Everybody got this? There's an answer. You're gonna have more decimals, of course, but you got it? That's good, good. 0.58. Yeah. Positive, as you were saying. Yeah. Yeah. And then that's it. Mm-hmm. Yeah. Mm-hmm. Oh, yeah, it's rounding off. Yeah. What happened? 7.5. Oh, that's what we found. That's what we found. Yeah. I'm actually going to talk about that a little bit real quick.
The only thing we plugged in was the 0.58 at the lower bound.
Yeah. And then the 1E99, and that's it. Yeah.
0.281.
Yeah, that's it. Yeah, that's it. Yeah. I mean, low key, that's your whole homework, the one question. But let's talk a little bit more. Forgetting your name. I'll talk after class. All right, so that's how we do our normal distribution, right? That's pretty much a 30 year test right there. That one example. So let's kick it up a notch, right? How does this result compare with the result we can obtain by using the formula for the binomial distribution when n is equal to 25 and p is equal to 0.25, right? Because remember we did the binomial PDF and binomial CDF. Let's compare these answers real quick. Got it done for you, so don't worry, don't worry. So check this out. So using the binomial distribution, right? From the 84 plus, love that calculator, right? And the N spiral, oh my God, right? Don't buy that, by the way. It's like 2 million, right? Anyway, they computed that the probability of R greater than or equal to 8 is equal to 0.2735. This means that the probability is approximately 0.27, that 8 or more of the water heaters will last at least 10 years. All right. So we used our normal distribution, and from our normal distribution, we approximated it to be about 0.28, right? The actual binomial distribution, remember when we do binomial CDF, right? The actual binomial distribution came out to be 0.27. Not too bad, right? It's off, of course, because it's an approximation, but not too bad, right? So that's what this lesson was about.
So it was the right answer from over in.
Mm.
You know, you right on that.
So like what your homework is doing tonight, right, is we're actually looking for the approximated answer, not the actual answer. But not last week's, a couple weeks ago, we were doing the binomial distribution, that was looking for the actual answer. Yeah. But right now, like our questions have become so ridiculous, with the number of successes and the sample size that we don't want to go through each individual one just to get that answer. Instead, we want to just use the normal distribution to approximate what that answer could be. Mhm. So how do the results in part A compare to the results in part B? Part B is the right answer, and part A was the approximation that we did, right? So let's talk about it a little bit. All right. So the error of approximation is the difference, right? Is the difference between the approximated normal value, which is 0.2810, and the binomial value, which is 0.2735. The error is only, and here's how we get the error. We just subtract it. 0.2810 minus 0.2735. We get 0.0075, right? Which is negligible, right? For most practical purposes, we knew in advance that the normal approximation to the binomial probability would be good since n times p, right, is 25 times 0.25 is equal to 6.25. And n, which is 25 times 0.75 is equal to 18.75. They're both greater than 5, right? So these are the conditions that assure us that the normal approximation will be sufficiently close to the binomial probability for most practical purposes. All right. Good stuff, good stuff. But let's talk about something that we mentioned earlier. Something that we kind of hinted at but glazed over. Right? So remember that when we use a normal distribution to approximate the binomial, we are computing the areas under the bars, right? The bar over the discrete variable r extends from r minus 0.5 to r plus 0.5, right? So this is the reason why we didn't use the 8, right? We use that 7.5, right? This means that the corresponding continuous normal variable x extends from r minus 0.5 to r plus 0.5, right? Adjusting the values of discrete random variables to obtain a corresponding range for a continuous random variable is called making a continuity correction, right? Continuity correction. We got to do it. We got to do it. We got to do it. All right. So this is how you do that continuity correction real quick. Gotcha. All right, so how to make the continuity correction. Convert the discrete random variable r, which is, remember, our number of successes, to the continuous normal random variable x by doing the following. If r is a left point, right, of an interval, subtract 0.5 to obtain the corresponding normal variable x. That is, x is equal to r minus 0.5, right? So what they're trying to say right there, right? I'm going to subtract 0.5 when I'm asking what's the probability of R greater than or equal to something. So let's write that in real quick.
When they say because you have to, I just think about.
Right.
0.5 positive.
Yeah. But just add this into your notes real quick. This is for the probability of R greater than or equal to some number, whatever. Right? If R is a right point of an interval, you're going to add 0.5 to it to obtain the corresponding normal variable x, that is, x is equal to R plus 0.5. This is the reverse, right? This is the probability of R less than or equal to some number. Right? Well, it's going to be, you're going to add 0.5, right? So imagine I want the probability. Let's say that I had a distribution like this, right? And there's bars here, right? There's bars here, like histogram bars, right? And I want the probability from here. Let's say R is equal to 5. I'm just making it up, right? And I want this area over here from 5, right? I have to pull it back a little bit, pull it back a little bit. So for less than, right? I'm going to add 0.5 to this. Just come over here. This is going to be x is equal to the 5, which is the R, plus the 0.5. Call that 5.5. And then now I've corrected the continuity. So now I can do that normal distribution going forward, like that. All right. All right, let's look at this.
Okay.
Go ahead. Oh yeah, we get into that. Yeah.
R is gonna be in that one.
I got you. Yeah. Yeah, I got you. We get into that. But one more thing, right? For instance, right? If we have the probability of 6 less than equal to R less than equal to 10. So now we in between two, right? We in between two, right? Where R is a binomial random variable and it is approximated by 5.5 less than equal to X, and it's gonna be X less than equal to 10.5, where X is the corresponding normal random variable. Just to show you where that's coming from real quick, right? Say I have a normal distribution like this, right? Again, we got bars here. We got bars, right? Let's just say hypothetically, right? Let's call that 6, and let's call that 10, right? And what do I want? I want the area in between them, right? So I want this area right here.
So 6 is on the left side and 10 is gonna be.
On the right side. Yeah.
So it's gonna be, like on the 10, you can plus 0.5 on this.
And the 6 you got to take away, right?
Yes.
Yeah. So that's it. So to get the 10, I'm gonna add 0.5 on this. Whoops, I wrote the wrong thing there. I'm gonna add 0.5 on this. And for the 6, I'm gonna subtract 0.5, right? To correct the continuity so that I can actually do the normal approximation for it. Right? So that's what that means. Yeah. But I know that my drawing is not very nice. Let me give you guys a better drawing. This is what I'm trying to say. Made that a little too big. Hold on.
That's gonna come like that. We had it.
No, this would be something you'd have to draw. Yeah. But yeah, this is the binomial distribution approximated to normal. And you see the 6 and the 10 is right here, right? But I want to cover all that area, right? So I got to subtract 0.5, bring it back here to where the end of the bar is, right? I gotta add 0.5 over here to bring it to where the end of the bar is. And then now I've corrected the continuity and I can find the area that I'm looking for. All right.
Does that mean that R is from 6 to 10, not 5.5 to 10.5?
R is from 6 to 10, right? But the thing is that to switch it to the X distribution, I have to extend it to cover the entire bar. And that's what I'm doing.
The X.
Just subtract 0.5 or add 0.5 to the R, and that's it. Yeah. Yeah. But going back up here though, right? If R is greater than, then you know what you're doing. You're subtracting 0.5. If R is less than, you adding it. Hmm? Well, from that, you have it as a normal distribution now, right? With the X, plug it in, little calculator, boom, and you're good to go.
What about, figure, 7, negative 35 on top?
Negative 35? Where? Yeah. Oh yeah, that's the figure. That's the figure. I was trying to draw it, but this is like a much prettier drawing to explain it, you know? Yeah, computers are really good artists. Who knew? You know?
Yeah, so.
Yeah. Mhm. Go ahead.
Did you go up to 14?
Up to the 14, because everything else beyond the 14 is like really, really small. It's so small we call it 0. That's why we're just cutting it off. But you're right. It should have went up to 25. You're right. You know, because that's my N. My N is 25. Mhm.
So the PR is gonna be 0.5 to 0.20, or is all the way more? On the graph, they're gonna call you on the PR on the left.
The NPR?
Down.
Down? Okay.
PR on the left side. 0.5.
On graph like
you, Mhm.
I'll be right.
Mm-hmm. The N over here is 25.
No,
Yeah.
on the PR on the left side.
Okay.
0.5, 0.10, 0.15, 0.20.
Oh, got you. The probabilities. This
Yeah.
part. Got you. Yeah. You're asking about the height, where they're coming
Yeah.
from and all that?
They're gonna, what's you on the,
Mhm.
on the diagram?
No. This is like for your benefit to see what's going on. Yeah, but remember that these heights are coming from doing the binomial distribution now. Remember the table that we had with that, right? So imagine that you did it for all the numbers from 0 to, like, in this case, 25, right? This would be the graph from there, and the highest bar is at 0.20, right? And then the lowest would be 0, of course, and then just get that. Yeah. Don't worry, I'm not gonna ask y'all histograms and all that, but I want y'all to understand. That's why. Yeah.
So. The table is going 0.14, right?
Mhm.
Supposed to be 0.225, right?
Mm-hmm. Oh, 0.25, no, that's way up there. That's not gonna be there. But 0.14 is like here somewhere.
So
Maybe like this one.
2020, so it's highest is like 2018, remember?
Yeah, about that.
Alright,
Probably
but
19. Yeah.
I'm confused now, so.
Yeah.
How we connect it? Okay,
Mhm.
the 6 with 0.20, how we connect that? So how we know like the 6 is gonna be more?
Oh, this one?
Yeah.
So the blue bar, this is the actual binomial distribution. Right? Remember when we do binomial PDF in the calculator? It's gonna give you what the answer for that. Yeah, remember your N is 25, your probability of success was 0.25, right? And then your no, excuse me, that was your P. Your
So
P was
basically-
0.25, and then your R is 6.
So basically on the calculator, they want 20,
It'll tell you everything. Yeah. What this is doing is it's like kind of overlapping two different distributions on top, right? The bars represent the binomial distribution, and the red line represents the normal distribution, right? That's what's happening over here. It's pretty cool, though. And then remember how our answer was a little bit larger than what the actual answer was, right? That's what this little space here is. See that yellow triangle stuff here? Right? When you add this up, that's the error that we had.
so you said the
Mhm. So the bars are the actual binomial distribution. Like that's the answer right there, right? And then the what's it called? The curve, right? The red curve is the normal distribution, the approximation to it. Mhm. This is good stuff, good stuff. So let's dig a little deeper real quick. I want to dig a little deeper. So what does a normal approximation to the binomial tell us? So a normal distribution can be used to approximate the probability of R successes out of n binomial trials. In order to use the normal approximation, the products n times p and n times q must both exceed 5, where n is the number of binomial trials and p is the probability of success on a single trial, and q is equal to 1 minus p. Unless n is fairly large, a continuity correction may be necessary in order to improve the approximation. All right. So that's the deep dive. That's what it's telling us, right? Let's switch gears a little bit. We're going to take it up a notch. All right. So we're going to talk about sampling distributions for proportions. Oh, it's going to be dope right here. So section 7.4, 7.5, we studied the sampling distributions for the mean. Now we have the tools to look at sampling distributions for proportions, right? Fractions. That's all that is, right? Remember when we do like general probability, so number of successes over the total number of everything? That's what this is, all right? So suppose we repeat a binomial experiment with n trials again and again and again, right? For each n trial, record the sample proportion of success, p hat, which is equal to r divided by n. Remember, r is your number of successes, n is your sample size, right? The p hat values form a sampling distribution for proportions. That's what we're getting into. This is fun, fun, fun stuff right here. Yeah. Which I'll be on bet 365 with this stuff now. All right. Hey, how about that Yankee loss? Damn, that shit hurt. I ain't gonna front, man.
Yeah, came to the.
Yeah. How about that presidential election? Damn.
Talking through.
Yeah, we just living in statistics right now, man. Yeah. All right, look at this. All right. So for sampling distribution for the proportion, right? P hat is equal to R divided by N. Given that N is equal to the number of binomial trials, which is a fixed constant, right? R is our number of successes. P is our probability of success on each trial, and Q, right? Remember, is the probability of failure on each trial, which is 1 minus P, right? Again, all on your formula sheet, right? If N times P is greater than 5 and N times Q is greater than 5, then the random variable P hat is equal to R divided by N can be approximated by a normal random variable X with the mean and standard deviation. So the mean for P hat is going to be equal to the P, right? Remember, P is just R divided by N. The standard deviation for P hat is equal to the square root of P times Q divided by N, right? All on your formula sheet. You don't got to memorize it. All right. So some good stuff right here. Let's talk about this. So the standard error for the P hat distribution is the standard deviation sigma P hat, right? Of the P hat sampling distribution. All right. And P is, proportion and all that. All right. Let's make a comment about this real quick. So to obtain the information regarding the sampling distribution for the proportion p hat is equal to r divided by n, we consider the sampling distribution for r, the number of successes out of n, the binomial trials. Earlier, we saw that n times p is greater than 5 and n times q is greater than 5. The r distribution is approximately normal, with the mean of mu for r is equal to n times p, and the standard deviation sigma r is equal to the square root of n times p times q. Notice that p hat is equal to r divided by n is a linear function of r. This means that the p hat distribution is also approximately normal when n times p and n times q are both greater than 5. In addition, from our work in the previous section with linear functions of random variables, we know that the mean for p hat is equal to the mean for r divided by n and n times p divided by n, which is equal to p. And the standard deviation, right, sigma p hat, is going to be equal to the standard deviation for the number of successes divided by n, or the square root of n times p times q divided by n, which becomes the square root of p times q divided by n. Although the values r divided by n are discrete for fixed n, we do not use a continuity correction for the p hat distribution. All right. This is the accepted standard practice for applications in inferential statistics, especially considering the requirements that n times p is greater than 5 and n times q greater than 5 are met, right? We see from the sampling distribution for proportions that the mean of the p hat distribution is p, the population proportion of successes. This means that p hat is an unbiased estimator for our proportion. All right? Good stuff right here.
Easy.
It is.
Yeah.
It is. Don't worry, we're gonna go through an example with this.
So it's not easy.
Yeah. So what does the p hat distribution tell us, right? Let's go over that real quick. Consider n binomial trials, right? We use p hat to be equal to r divided by n to estimate, right, our proportion p, the population probability of successes on a single trial, where r is our number of successes out of n binomial trials. To create a p hat distribution, repeated set of n binomial trials must be conducted to determine individual sample statistics p hat. Fortunately, mathematics can be used to obtain the following information, right? So for n times p greater than 5 and n times q greater than 5, the p hat distribution is approximately normal. The mean of the resultant p hat distribution is p, right? And the standard deviation, also known as a standard error, is a square root of n of p times q divided by n, where q is equal to 1 minus p. Good stuff, good stuff, good stuff. All right. Let's take a look at an example real quick. One topic. All right. So sampling distribution of p hat, right? How you doing? So the annual crime rate in the Capitol Hill neighborhood of Denver is 111 victims per 1,000 residents. This means that 111 out of 1,000 residents have been a victim of at least one crime. That sucks. For more information, right, visit the whatever website, right? These crimes range from relatively minor crimes, right? Stolen hubcaps or purse snatching, to major crimes, which is like murder. The Arms, right, is an apartment building in the neighborhood that has 50-year round residents, right? Suppose we view each of the n equals 50 residents as a binomial trial. The random variable r, which takes on the value 0 to 50, represents the number of victims of at least one crime in the next year. Okay. So kind of a morbid story, but we're gonna look at it. So here's what I want to know. Here's the question. from the story. Right? So what is the population probability P that a resident in the Capitol Hill neighborhood will be a victim of a crime next year? And what is the probability Q, right? Failure, that a resident will not be a victim of the crime? All right? Q sounds nicer than P right now. Not gonna lie. All right. So using the report, we take that P is going to be equal to 111 divided by the 1,000, right? Which is equal to 0.111. And the probability of you not being a victim of crime is going to be 1 minus, right, the 0.111, which gives us 0.889. All right. All right, so consider the random variable P hat is equal to R divided by N, right, which is equal to R over 50, right? 50 is how many residents we have in the place, right? Can we approximate the P hat distribution with a normal distribution and explain, right? So here we go. So we do N times P, N is 50 times 0.11, and that's going to be equal to 5.55. We do N times Q, which is going to be the 50 times 0.889, and we get 44.5, right? Since both the N times P and the N times Q are greater than 5, we can approximate the P hat distribution with a normal distribution. That's the verify that we can actually do something with this. Mhm. So here's our next question right here. Go ahead.
It's under 5.
Then we can't use the normal distribution to approximate it. Yeah.
Always greater than 5. Right?
Not always. If it's less than 5, you have to do something else. Maybe you have to do a binomial distribution for this, you know. But when it's greater than 5, we're good. If it was real life and it was less than 5, and you wanted to kind of make it so that it would be greater than 5, the answer to that question would be to increase your sample size, right? So right now you're talking about 50 in one building. Maybe you need to get 2 more buildings involved, right? Say 50, 50, 50. Now you have 150 people, right? So that would probably push it even bigger than the 5, you know? If you had to do an experiment in real life.
Before you go,
Yeah.
can you go to number 8 first?
Which one?
Number 8, first one.
This one, got you.
Equation.
Uh-huh.
No, go. One of your questions.
Oh, got you. Hmm. You're welcome. No problem. All right, let's look at the next question, right? So the next question that we have, right? What are the mean and standard deviations for the p hat distribution? All right. So let's take a look at that. So our mean, right? Mu p hat is going to be p is equal to 0.11. We did that already. That's just like the n times p, basically. Our standard deviation for p hat is going to be the square root of p times q divided by n. You just kind of plug them in, boom, boom, and you're going to get that on the calculator, right? And then after that, you can use a normal distribution to find whatever, right? What's the likelihood that they'll be attacked? Or what's the likelihood that they won't be attacked? What's the likelihood that 5 of them will be attacked? What's the likelihood that say 10 of them won't be attacked? We can do all that math given that we have our mean and our standard deviation using the normal approximation. All right. So
So number C don't have nothing to do with number B, so number C always gonna
something
be
different.
connected to number A.
Right. For the story. So this is the last topic for what's going to be on the test next week. All right. Questions about it?
The last topic you said? So
Mhm.
it's gonna be the last part.
Yeah. Well, it's gonna be the last part of the test.
Can
Yeah.
you say, can
Yeah.
you read all the test?
I got you. I'm gonna after class, I'm gonna make a like a review sheet of all the topics that's gonna be on the test. I'm gonna send that out. But I'm gonna do it in an announcement with the recording. Yeah, that's what I'm saying. I'm gonna create it and send it to you guys. Yeah. It's not gonna be like right after class, because I gotta go work. Yeah. But you guys are gonna get it today, like as an announcement with the recording and everything. It'll be there. All right. For the test, remember you could use your formula sheet, your calculators, right? Calculators are really important now. Just type it in and get the answer, and that's it. You know? Yeah, about the homework for this, I apologize. I only got one question, But yeah. Oh no, the 1 for 3 we're about to get to right now. Yeah. So the next topic we're about to do right now, this is not on the test, but I don't want to waste the class time, because we got more time. So yeah. But at the end of class, if y'all want to stay back, we could knock out the homework together if y'all want, all 4 questions, call it a day. Yeah. Yeah. All right, so at the end of class, we'll do that. All right. So let's jump into our next topic, right? This is for the third test. That's what we're starting right now, right? So not the biggest fan of this topic, but there's some good information still. Right? Chapter 8. Yeah. So we about to talk about estimation right here, right? More specifically, we want to estimate the population mean mu when we know what the population standard deviation is, right? Bullshit, but whatever. We're gonna go through it. All right. Yeah. All right. This is what we're getting into right now. I don't even like that title. I'm gonna just pull that off, right? So because of time and money constraints, right? Difficulty in finding population members and so forth, we usually do not have access to all measurements of an entire population. Instead, we rely on information from a sample. In this section, we develop techniques for estimating the population mean mu using sample data. All right. We assume the population standard deviation sigma is known. Let's begin by listing some basic assumptions used in the development of our formulas for estimating mu when sigma is known. There's some good stuff right here. Oh, they always tell me not to assume, but we about to make some assumptions. We're about to make some assumptions. All right, so assumptions about the random variable x. We have a simple random sample of size n drawn from a population of x values. The value of sigma, the population standard deviation of x, is known. And if the x distribution is normal, then our methods work for any sample size n. If x has an unknown distribution, then we require a sample size of n to be greater than or equal to 30. However, if the x distribution is distinctly skewed and definitely not mound shaped, a sample size of 50 or even 100 or higher may be necessary. All right. So that's what we're getting into. And I know this gonna seem so easy. Y'all gonna wish dang, couldn't this be on the test? But I got y'all with the next test. All right. So an estimate of a population parameter given by a single number is called a point estimate for that parameter. it will come as no great surprise that we use X bar, the sample mean, as a point estimate for mu, the population mean, right? So basically, like I know what X bar is, and I assume that that's what the population mean is, right? Let me just elaborate on point estimate a little bit real quick. New topic, so new vocabulary. A point estimate of a population parameter is an estimate of the parameter using a single number. X bar is the point estimate for mu. All right.
This stuff is gonna be in the final.
Oh yeah, most definitely. Yeah, yeah. But it's real simple though.
Mhm.
Yeah. Like when you look at your homework, you're gonna see how simple it is. You know?
Yeah.
So even even with the large random sample, the value of X bar usually is not exactly equal to the population mean mu. The margin of error is the magnitude of the difference between the sample point estimate and the true population parameter value. All right. Let's look. Go ahead.
You know that, somebody of that, go home and be back, and it's like that.
Yeah, you can still do that. You have time.
No,
Yeah.
we like.
Mhm.
Well, the people want,
Like you want extra homework?
yeah, like some days, like we had to do online.
Yeah.
Everybody went home.
Yeah.
Everybody, next hour,
But verify it with the tutor before you do that. That's the only thing. Yeah, yeah. The test corrections. Yeah, yeah, yeah. I mean, you could do it after class though, right? Like tutoring opens up at 12. You know, just go in there like, yo, check this over, sign it, and then just bring it back to me. Because you know I'm here. I'm not leaving. Yeah. All right, so when using X bar as a point estimate for mu, right? The margin of error is the magnitude of X bar minus mu, or the absolute value of X bar minus mu, right? Absolute value is basically like a measure of how far a number is from zero, right? So absolute value is always positive, right? So I want to know how much error is in my answer, right? Plus or minus. Mhm. So we cannot say exactly how close X bar is to mu when mu is unknown. Therefore, the exact margin of error is unknown when the population parameter is unknown. Of course, mu is usually not known, or there would be no need to estimate. In this section, we will use the language of probability to give us an idea of the size of the margin of error, right? We use X bar as a point estimate for mu. First, we need to learn about confidence levels, right? The reliability of an estimate will be measured by the confidence level, right? Gotcha. So suppose we want a confidence level of C, all right? Theoretically, we can choose C to be any value between 0 and 1, but usually C is equal to a number such as 0 0.90, 0 0.95, or 0 0.99. In each case, the value of Z critical is the number such that the area under, and continue real quick. Sorry. The area under the standard normal curve, right, falling between negative Z critical and positive Z critical is equal to the critical value. So the value for Z critical is called the critical value for a confidence level of C. All right. I just want to graphically show you guys what this means real quick. All right. So let's say I have a confidence level C, right? So some random confidence level, right? This is the normal distribution right here, right? And I'm interested to know what is that Z critical value, right? So I'm kind of doing a little bit of a reverse. Remember when we did the inverse normal, right? From last chapter, right? Or last section. That's what we're doing here to find Z critical, right? And then that's it. It's easier to find negative Z critical and then just make it positive, right? They're the same numbers, right? If this is 3 and this is -3, and if this is 2 and this is -2, same numbers. Mm-hmm. Bless you. It's that time of year. So for a confidence level C, the critical value, which is Z critical, is the number such that the area under the standard normal curve between negative Z critical and positive Z critical equals the critical value. Or the confidence level, whatever. All right. So the area under the normal curve from negative Z critical to positive Z critical is the probability that the standardized normal variable Z lies in the interval. This means that the probability of negative Z critical less than Z less than the Z critical is equal to the confidence level, right? Or C, yeah. If it's okay, I want to just jump into an example real quick. So in this example, right, we want to find a critical value. Right, so we're going to use table 3 of the appendix, whatever, to find a number for Z 0.99, right, such that 99% of the area under the standard normal curve lies between, let's do, negative Z for 0.99 and positive Z for 0.99, right? So this is, we will find Z 0.99 such that the probability of negative Z 0.99 less than Z less than Z 0.99 is equal to 0.99. Let me draw this real quick so you guys can get an idea, right? Say I have a normal distribution here, right? This is negative ZC. And this is positive Z critical right here, right? And what I'm telling you, right, in this particular question we're talking about, right? This would be my area under the curve, 0.99, right? So I want to know what Z value corresponds to 0.99 in the middle, in between these two values. Mm-hmm. All right, so the previous section, we saw how to find the Z value when we're given an area between negative Z and Z. The first thing we did was to find the corresponding area to the left of negative Z. If A is the area between negative Z and Z, then 1 minus the area divided by 2 is the area to the left of Z. In our case, the area between negative Z and Z is 0.99. The corresponding area to the left tail is 1 minus 0.99 divided by 2, right? So what they're trying to say right here, if I do, excuse me, if I do 1 minus 0.99, right? You take 99 pennies from a dollar, right? You're gonna have a penny left, right? 0.01. Now that corresponds to the area to the right over here and the area to the left over here. So what we have to do is cut the penny in half, right? Now we're looking at like some bank interest type shit, right? Cut that in half. So now that's the 0.005, right? That's what this area over here is, 0.005. And this one right here, 0.005, right? So what we're saying is it's easier to look up the negative ZC, right? To figure out what that is. And then when you get that answer, just make it positive, and that's your positive Z critical right there, right? Before I jump to the answer though, let's try and do that in the calculator real quick. Little blast from the past, all right? Give me 1 second. Let me get my calculator real quick. My fault. Sorry about that. Nope, that's not it. 1 second. All right, we good to go. All right. So here's what we're gonna do for this one right here. I want that negative ZC, right? That's what I'm looking for. Negative ZC, right? You're gonna hit second, and we're gonna hit the data button right there, right? So second, then we're gonna hit the data button. And then you're gonna go down. That's the down key right there, right? We want to go down to where it says inverse normal or normal inverse. I forget what it says. Somebody tell me. What is it? Is it inverse normal or normal inverse? Inverse is spelled INV. You don't see that there?
Yeah. Inverse normal.
Inverse normal, INV, right? All right, so you're gonna go down to INV norm, right?
You have error means.
Good. So over here, right? For our area. The area is what we found up here in the graph, right? That's it. Because remember, I want to get that negative Z critical right here. That's the 0.005, right? Write that down. That's the 0.005. What's my mean, right? So mean. What do we think my mean is going to be?
0.01.
No,
There,
0, right? Because these are Z's, right? So whenever we have a normal distribution, mean is 0. And what's my standard deviation? Good. Perfect. Press enter. What you guys got?
75.
2.5, 75, 82. Okay. All right. So which one? No, yours is a little bit different. So for you, you put your area first. You got 0.005. Then you're going to do comma. That's the comma right there. 0, comma 1, close parentheses, enter. And there you go. Okay. Yeah. Okay. So what you got to do, you got to write down like this thing. All right. Because you're going to have to memorize that. Yeah. Or if you want, form a sheet, just write it on there. Yeah, that's fine. Yeah. All right. Anyway, long story short, right? I found negative 2.57582, right? Now, if I wanted to find the positive Z value, remember this is negative Z, C, right? Positive ZC is the same number without the negative. That's it. 2.57582. That's it.
Yeah.
Yeah.
Round it.
If you want to, I'm not a fan of rounding, but yeah, if you want to.
Oh.
If you are gonna round it, get rounded off to like the nearest hundredth place.
Can you go
So
up, please?
2.58. Over to the graph up here. That's what you want
Yeah,
to see?
please.
Got you. Yeah. Right. It's gonna be positive, and I'm gonna plug it into a formula. Well, I'm getting to that, right?
Let me know.
Mm-hmm.
Okay.
Got you.
0.005.
Got you. So look, I'm looking for an area, right? For 99%. That's my confidence level. 99%. Right? The 99% is always going to be right here in the middle, right? And that 99 could change. It could be 89, it could be 54, whatever, right? It's going to be in the middle. That's just the point of it, right? And then what I want to do is I want to find the negative Z critical. That's just the easier thing to do, right? So whatever the 99 wants to be, I'm going to do 1 minus it, right? 1 minus it. That's going to give me the area here, right? But that area is both of these areas on the sides added up together, right? So I have to divide it by 2 to get the individual areas for each one, right? So boom, now I got the 0.05. This is the area I could type into my calculator to give me negative Z critical, right? And then I just have to remember, oh wait, I want the positive version of that. So I'll just make it positive and that's it.
So the mean always gonna be 0. Right?
Yeah. For a normal distribution with Z, yes. Yeah.
The other one is
And the X distribution is not so, but for a normal distribution, the mean is always 0. And the standard deviation is 1. I mean, I'm over here trying to draw, but my drawing is not that nice. So for those who couldn't see it and understand it, this is what I was trying to do. All right, so the areas between negative Z and positive Z is 0.99, as you can see right here, right? And then I found the area to the left over here, which is a 0.005, and I'm using that to find a negative Z value. That's it. I'm sorry? Oh, because that's what they asked. That's the confidence level they asked. Yeah, that's always going to be given to you.
What is the whole thing?
Yeah. The whole thing is 1. Yeah, yeah. So that's the reason why I'm subtracting it from 1 to find them other areas. That's right there. And so next, we're going to use a table, right, to find the value, to find the Z value corresponding to the left tail area of 0.005, right? So now let's say you don't have the calculator and you want to just do it on the table. That's how to do it right here, right? So we see that the desired area is 0.0050, right? Because remember, the table has 4 decimal places after it, right? Right, is exactly halfway between the areas. So when we look at the table, we're going to get that Z is equal to negative 2.58, right? And Z is equal to negative 2.57. Because the two area values are so close together, we use the more conservative Z value, which is the negative 2.58, rather than interpolating, right? So in fact, Z for 0.99 is 2.576, right? However, to 2 decimal places, we use Z for 0.99 equal to 2.58 as the critical value for a confidence level of C is equal to 0.99. So we have the probability of negative 2.58 less than Z less than 2.58 is similar to 0.99, our critical value. All right. Let me just show you guys the table real quick and what they're saying. This is if you don't have the calculator. Boom, right? So you guys remember the normal distribution table? That's what I'm talking about from right here. What you have to do in the middle of the table is you have to find where is that probability, right? Ours is going to be 0.0050. You have to find where it is. And what's going to happen more often than not, it's going to be in between two numbers. In this case, it's in between this number 0.0051 and 0.0049, right? Now, that being said, right, this is 0.0051 is negative 2.57, and 0.0049 is negative 2.58. That's where they get both of those numbers from. All right,
Question,
go ahead.
if C
Mhm.
0.99 is equal to 2.576, right?
2.58, yeah.
And the calculator was 2.57582.
Which we're just rounding it off, yeah, because of the yeah. But you can use that entire number. You don't have to like round it off if you don't want to. Like I don't round off when I do my stuff. Mhm.
So the last number,
Mhm.
so it's 575, right?
Mhm.
So the last number, you can put it between, oh, one point.
Yeah.
So the next number is gonna be, oh, the five, something like 82.
82. What do you mean? All right, we'll look. Worst case scenario, just copy from the calculator. You never get it wrong. Mhm. All right, so look, the results in example one will be used a great deal in our later work, right? So for convenience, there's another table, A2, which gives you some levels of confidence and critical values for Z critical. The same information is provided in another table of the appendix. An estimate is not very valuable unless we have some kind of measure of how good it is, right? The language of probability can give us an idea of the size of the margin of error caused by using the sample mean X bar as an estimate for the population mean. Remember that X bar is a random variable. Each time we draw a sample size N from a population, we get a different value for X bar. All right? So according to the central limit theorem, right, if the sample size is large, then X bar has a distribution that is approximately normal with mean mu X bar is equal to mu and population mean we are trying to estimate and the standard deviation sigma X bar, which is equal to sigma divided by the square root of N. If X has a normal distribution, these results are true for any sample size, right? So this information together, right? This information together with our work on confidence levels leads us to the shown as the in the optimal deviation that follows, right? For the probability statement. So the probability of negative Z critical times the population standard deviation divided by the square root of N is less than, right? X bar minus mu, which is less than Z critical times the standard deviation divided by the square root of N. And this is going to be equal to our confidence level. Mhm. Very, very theoretical stuff going on here. All right. Real quick, let me show you this table that you all have in your formula sheet. All right. It's table 8.2, right? These are some of the level of confidences corresponding Z values. So for a confidence level of, let's say, 75% or 0.75, you can say that the Z critical value is 1.15, right? This is if you don't want to go through that whole process of doing the inverse normal to find it and stuff like that. But it only works for these given confidence levels. So if you see a confidence level that's not here, you have to use that other process, the inverse normal, to get the actual Z critical that I'm looking for. All right. But you all have this. It's on, if you look at the normal distribution table, the positive side, the very bottom, this on the left, that's where this table is right there. Right? So that's going to help you to find your Z critical values. Y'all will see that in the homework tonight. Good stuff. All right, so equation 1 uses the language of probability to give us an idea of the size of the margin of error for the corresponding confidence level C. In other words, equation 1 states that the probability is C, that our point estimate X bar is within a distance of plus or minus Z critical times the standard, the population standard deviation divided by the square root of N of the population mean mu. This relationship is shown, right? In the following optional discussion, right? We're going to derive where this is coming from, right? This is going to be some good stuff right here. Yeah, let me start off with this graph real quick. And then we're going to jump into it. So this is the distribution of the sample means X bar, right? The probability that the critical value for X bar is within plus or minus Z critical times the standard deviation divided by the square root of N of the true population mean mu, right? So this is the proportion of the total area, the critical value, and these are the Z's that I'm trying to find for it. That's simple. All right. All right. So for a confidence level C, right, we know that the probability for negative Z critical less than Z critical is going to be the critical value. This statement gives us information about the size of Z, but we want information about the size of X bar minus mu, right? That error. So is there a relationship between Z and X bar minus mu? The answer is yes, since by the central limit theorem, X bar has a distribution that is approximately normal with mean mu and standard deviation sigma divided by the square root of N. We can convert X bar to a standard Z score by using our Z formula. Z is equal to X bar minus mu over standard deviation over the square root of N, right? Really important formula. Gonna be on your test next week. Just let y'all know. All right. Substituting the expression for Z into equation 2 gives us the probability of negative Z critical is less than X bar minus mu over the standard deviation divided by the square root of N less than Z critical, which is the critical value. Multiplying all parts of the inequality right up here by the standard deviation divided by the square root of N gives us this formula we just looked at, right? This is the probability of negative Z critical times the standard deviation over the square root of N less than X bar minus mu less than Z critical divided by times the standard deviation divided by the square root of N, which will give us our critical value, right? So equation 1 is precisely the equation that we set to derive. So some good stuff here, good stuff. All right. Let's get to the meat and potatoes right here, right? So the margin of error, right? So the margin of error or absolute error, right? Absolute value. There you go, right? Using the X bar as a point estimate for mu is the absolute value of X bar minus mu. In most practical problems, mu is unknown, so the margin of error is also unknown. However, equation 1 allows us to compute an error tolerance, E, that serves as a bound on the margin of error. So using the confidence level, right, which is like C with the percentage, we can say that the point estimate X bar differs from the population mean mu by a maximal margin of error, E is equal to Z critical times the standard deviation divided by the square root of N. Remember this, really important formula right here. This is on your formula sheet. This is chapter 8, the next side, right? It's right there. That's the first formula right there. Oh, we about to go deep right now. There's some good stuff right here. All right, so take a note, right? Formula 5, right? Which is this one right here. All right. For E is based on the fact that the sampling distribution for X bar is exactly normal, right? With mean mu and standard deviation sigma over the square root of n. This occurs whenever the X distribution is normal with mean mu and standard deviation sigma. If the X distribution is not normal, then according to the central limit theorem, large samples of n is greater than or equal to 30 produce an X bar distribution that is approximately normal with mean mu and standard deviation sigma over the square root of n. All right. So using the two equations, we conclude, right, that we have the negative E value here less than X bar minus mu less than the positive E value is equal to the confidence level. All right. Oh, let's take it up a notch right after that. This is where we get into. We'll get into that formula sheet formula right there. All right. So equation 6 states that the probability is C, right? That the difference between X bar and mu is no more than the maximal error tolerance E, right? So if we use a little algebra on the inequality, right? We have negative E less than X bar minus mu less than E, right? For mu, we can rewrite it in the following mathematical equivalency way as X bar minus the error less than mu less than X bar plus the error. This is what's on your formula sheet. This formula right here. You guys can see that, chapter 8, next side on the formula sheet, right? So since formula 7 and 8 are mathematically equivalent, their probabilities are the same. Therefore, from 6, 7, and 8, we obtain that the probability of X bar minus E less than mu less than X bar plus E is equal to your confidence level. All right. This is some good stuff right here. And it's really, really simple when you put it all together and do it. Promise you, promise you. All right. So equation 9 states that there's a chance, right, confidence level, that the interval from X bar minus E to X bar plus E contains the population mean mu. And we call this interval a C confidence interval for mu, right? So that's what this is, the confidence interval for our population parameter mu. Mic drop. Ooh. All right. So let's keep it going. A C confidence interval for mu is an interval computed from sample data in such a way that C is the probability of generating an interval containing the actual value of mu. In other words, C is the proportion of confidence intervals based on random samples of size n that actually contain the mean mu, right? So what's happening here, right? I'm taking many, many samples, right? I don't know what the population parameter is, right? I don't know what mu is, but I want to know, right? So what this formula is allowing me to do is allowing me to estimate what mu could be, right? From all the samples that I took, right? And based on my level of confidence that I choose, or they're going to tell you what that is actually, right? I could say with a certain level of certainty that the estimate, the range that I believe, right, the population mean might be in will contain the actual mean. Is it always going to contain the mean? No, but is a possibility. There's a highly likely chance that it will contain it, right? And how likely is it? It's my confidence level. And that's what this is. There's some good stuff right here. Good stuff. So we may get a different confidence interval for each different sample that is taken. Some intervals will contain the population mean mu and others will not. However, in the long run, the proportion, right, of confidence intervals that contain mu is the confidence level. Yeah, some good stuff right here. All right, let me show y'all how to do it real quick. Then we're gonna jump into an example. Let me show y'all how to do it real quick. All right. So the procedure right here. This is how to find the confidence interval when mu when the standard deviation is known. Right. This is what your homework is right here. Right. So requirements: let X be a random variable appropriate to your application. Obtain a simple random sample of size n, right, for X values from which you compute the sample mean X bar. The value of sigma is already known, perhaps from a previous study. If you can assume that X has a normal distribution, then any sample size n will work. And if you cannot assume this, then use a sample size for n greater than or equal to 30, right? That's what unlocks it. So confidence interval for mu when sigma is known, right? We have our formula on the formula sheet. This is X bar minus E less than mu less than X bar plus E, right? E is your margin of error, where X bar is equal to the sample mean of the random sample, the simple random sample, excuse me. E, our margin of error, is equal to Z critical times the standard deviation divided by the square root of n. You'll be given all that information. Our confidence level, which you'll be given, is going to always be between 0 and 1, right? And then we have our critical value, which is what we have to find. That's the hard part, right? Our Z critical value for confidence level C based on a standard normal distribution, right? And we can use the appendix whenever applicable, but sometimes, you might get a confidence level that's not on there, and then you have to do the inverse norm to get the actual value, right? All right, let's take a look. Let's look at an example real quick. This example is what your homework's going to be about. All right. This is going to be a confidence interval for mu with sigma known. So Julia enjoys jogging. She has been jogging over a period of several years, during which time her physical condition has remained constantly good. Usually she jogs about 2 miles per day, with the standard deviation of her times is sigma is equal to 1.880 minutes, right? During the past year, Julia has recorded her times to run 2 miles, right? She has a random sample of 90 of those times. Damn. For these 90 times, the mean, right, was X bar is equal to 15.60 minutes, right? Let mu be the mean jogging time for the entire distribution of Julia's 2-mile running times. So taken over the past year, find a 0.95% confidence interval for mu, right? So I want to find a confidence interval for mu, right, using a confidence level of 0.95. Let's take a look at how to do that. It's going to be good right here. All right. Just blow that up real quick. Make it readable. All right. So we have a simple random sample of running times, right? And the sample size n is equal to 90. It's large enough for the X distribution to be approximately normal. So we know that sigma, excuse me, right? We also know sigma. It is appropriate to use the normal distribution to compute a confidence interval for the mean mu. So to compute the margin of error E, right, for a 95% confidence interval for X bar minus E to X bar plus E, we use the fact that Z critical is equal to 1.96. So if you look at the table, right, in your formula sheet, right, for a 95% confidence level or 0.95, whatever, the Z critical value for that is 1.96. So that's where we're getting the 1.96 right here, right? Together with the values of n is equal to 90 and the standard deviation equals to 1.8, we just plug it all in. Straight calculator. 1.96 times 1.8 divided by the square root of 90, boom. We get 0.37. So using the equation, it's that simple. The given value of X bar, plug it in. X bar is 15.60, 15.60. Our margin of error that we just found, 0.37, right? 0.37. You're going to subtract on the left, add on the right. That's it. Your final answer is this line right here. 15.23 less than mu, less than 15.97. Right? That's all I'm looking for. That's your whole answer right there. And that's it. All right. Simple, simple, simple. All right. I do want you guys to understand it though. So let me interpret this a little bit. So we conclude that with a 95% level of confidence that the interval from 15.23 minutes to 15.93 minutes is one that contains the population mean mu of the jogging times for Julia. Right? So we don't know if the sample will contain it, but we believe that 95% of the time when we take a sample, it's going to have the sample mean inside of it. Very important.
Like, percent, right? We're gonna have like 90 and 30%.
Sometimes. In real life, it could be different. All right. If it was real life, you might have to use the inverse normal to find the actual Z critical that you're looking for. So let's talk about the interpreting this a little bit, right? So a few comments are in order about the general meaning of the term confidence interval. So since X bar is a random variable, the endpoints X bar plus or minus E are also random variables. Equation 9 states that we have a chance for C of obtaining a sample such that the interval, once it is computed, will contain the parameter mu. After the confidence level is numerically fixed for a specific sample, it either does or does not contain mu. So the probability is 1 or 0 that the interval, when it is fixed, will contain mu. All right. A couple more comments to be made. Okay. A non-trivial probability statement can be made only about variables, not constraints, right? So equation 9, which is the probability of X bar minus E less than mu less than X bar plus E is equal to the confidence level, really states that if we draw many random samples of size n and get lots of confidence intervals, then the proportion of all the intervals that will turn out to contain the mean mu is the confidence level. So for example, right, in the figure that we're going to show in a second, the horizontal lines represents 0.90 confidence intervals for various samples of the same size from an X distribution. Some of these intervals contain mu, others do not. Since the intervals are 0.90 confidence intervals, about 90% of all such intervals contain mu, right? For each sample, the interval goes from X bar minus E to X bar plus E, all right? So let me just show you guys graphically real quick what I'm talking about here. This is really, really dope. So I don't know what the population mean is, right? But from here, I can actually estimate it. So this is a graph of a 90% confidence interval, right? From X bar minus E to X bar plus E. So each one of these are ranges, different ranges for different samples that were taken, right? And I am 90% confident, right, that the mean falls in between each one of these ranges. This right here where mu is, this is the actual mean right here. That's the actual mean. You see, some samples don't even have the mean, right? Other samples, they have it, and it's real close to it, right? There's no perfect sample here. This one look kind of perfect, but there's no perfect sample here. You know, to have a perfect sample would mean to be able to test everything, right? Let me see, real life example that I could give you guys, right? We just went through an election, right? Now, in regards to the election, you go to different places. You go to the Bronx, you go to Wyoming, you go to California, different places, right? You're not testing the whole state, right? But you're testing a little piece of the state, right? Like if it was New York, you're just testing the Bronx, for example, right? And you want to know how do they feel, like which candidate they're gonna go for, right? Now, we want to know how does the country feel, right? But it's impossible for us to get country numbers. So what we could do is we could take a small sample space like the Bronx and use that to estimate what the country might be feeling. All right. So that's what this is right here that we're doing. Want to make some more comments real quick. So once we have a specific confidence interval for mu, such as 3 less than mu less than 5, we can say, all we can say is that we are C% confident that we have one of the intervals that actually contains mu. Another appropriate statement is that at the C confidence level, our interval is one that contains mu. Hmm. So let's talk about this, right? What does a confidence interval actually tell us, right? So a confidence interval gives us a range of values for a parameter. A confidence interval for a parameter is based on a corresponding sample statistic from a random sample of a specified size n. A confidence interval depends on a confidence level C. Common values for C are 0.90, 0.95, and 0.99. If we take all possible samples of size n from a population and compute a C confidence interval, for each sample, then the C confidence percent, right, of all such confidence intervals will actually contain the population parameter in question. Similarly, 1 minus the confidence level of a confidence interval will not contain the parameter. All right. So when we use samples to estimate the mean of the population, we generate a small error. However, samples are useful even when it is possible to survey the entire population because the use of the sample may yield savings of time or effort in collecting data. All right. All right, this next point is going to be real cool. This is going to be real dope right here. All right, check this out, right? So now we're going to look at a sample size for estimating the mean mu, right? And this is going back to someone's question over here. I don't remember who asked it, right? So in the design stages of statistical research projects, it is a good idea to decide in advance on the confidence level you wish to use and to select the maximal margin of error E you want for your project. However, how you choose to make these decisions depends on the requirements of the project and the practical nature of the problem. Whatever specifications you make, the next step is to develop the sample size. So solving the formula that gives the maximal margin of error E for N enables us to determine the minimal sample size, right? So this is really, really dope. So say we're about to run an experiment, right? And I'm gonna just say what kind of confidence I want to be, like how confident I want to be in finding my parameter, right? I can actually reverse engineer the formula so that I can determine how large of a sample do I need to get that level of confidence in my answer, right? This is real dope right here. So check this out. This too is on your formula sheet as well. All right. So this is the procedure. This is how to find the sample size N for estimating the population parameter mu when we know what sigma is, right? So here's the requirements. The distribution of the sample means X bar is approximately normal, right? We have to assume that, or we need that requirement. The formula for the sample size right here, right? We want to know what N is. How large of a sample do I need to run my experiment? I know what Z critical is, right? And I know what my margin of error is because I'm making that up, right? And I know what my population standard deviation is. Then you're going to square it and boom, you're going to have your answer. So E is our specified maximal margin of error. Sigma is our population standard deviation. Z critical, right, is our critical value from the normal distribution for the desired confidence level. Commonly used values for Z critical can be found on the table. We know that. If N is not a whole number, increase N to the next higher whole number. That's important right there. If N is not a whole number, increase N to the next higher whole number. Note that N is the minimal sample size for a specified confidence level, and the maximal error of estimate is E. Good stuff, good stuff, good stuff. All right. So if you have a preliminary study involving a sample size of 30 or larger, then for most practical purposes, it is safe to approximate sigma with the sample standard deviation S in the formula for sample size. All right. Nice little comment right there. But real quick, let's run through an example real quick. And then we could call it at that. Real quick example. So we want to take the sample size for estimating mu, right? A wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company, right? A preliminary study of a random sample of 50 salmon showed that S is equal to 2.15 pounds. How large a sample should be taken to be 99% confident that the sample mean X bar is within 0.2 pounds of the true mean weight of the salmon, mu, right? So here we go. How large of a sample do we need? Got y'all right here. So in this problem, right, we want to be 99% confident, right? So we're looking for Z 0.99, and we know that that's going to be equal to 2.58 from the table, right? And our margin of error that we want is 0.2, right? The preliminary study of 50 fish is large enough to permit a good approximation for sigma by the sample standard deviation being 2.15. Therefore, we're gonna use this equation right here, right? We're gonna plug in our Z critical, which is 2.58. We have our sample standard deviation, which we got to be 2.15, and we know that our error that we are allowing ourselves is 0.2. When we do the math on that, also you have to square it when you're done. When we're doing the math on that, we come out to 767.2, right? So in determining the sample size, any fractional value of n is always rounded to the next higher whole number. We conclude that a sample size of 770 will be large enough to satisfy the specifications. Of course, a sample size larger than 770 also works, right? So I can only take whole number samples, right? That's why I have to round this up, right? And this answer that I'm getting right here is the smallest possible sample that I could take to get my final answer, right? And that's it. That's the whole sample size thing. Questions on this? Anybody? All right. I'm gonna stop the recording. If you guys want to do your homework, take it out. I can knock it out right now. It's only like 4 questions. Next week, test, right? We have chapter 5, chapter 6, chapter 7, right? Remember, you have your contingency tables, the and the or stuff. That's chapter 5. Binomial distribution, right? That's a discrete probability distributions. And then we have our normal distribution or our continuous distributions right there. Use your formula sheet, use the calculator, you're good to go. All right. They can show up later. All right, so I'm gonna stop the recording. If that's good with everybody. And I can take this down. All right. Those of you that's listening, have a good night. See you guys next week. Oh, my fault. I'm sorry. My fault. Go ahead.
I'm watching the videos trying to like catch up.
Go ahead. You want to take a picture?
Yeah, I'm gonna take a picture of that.
My
I'm
fault,
watching the
man.
videos currently right now.
Yeah.
Everything you posted on YouTube. So
Yeah.
that shit is OD helpful, bro, for me, because I know
I'm
this
glad.
test right now. You gonna need that shit. But for sure, if you
got
got office hours today,
Yeah.
if you're gonna be in there at 3 o'clock, I'm gonna pull up right at 3. So
Yeah, I'm gonna be there.
yeah, for sure, I'm gonna pull up every today.
Yeah. All right, take a picture real quick because I wanna stop this so I can download it to post it for y'all.
For sure.
Yeah. One second real quick.